Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Nex AGI Team Custom PDF, Nex N1 Agentic Scaling Infrastructure. This paper tackles the gap between today's large language models and truly autonomous agents. Standard LLMs are trained to predict the next token, which makes them strong at answering questions but weak at planning and acting over long horizons. Real agentic tasks like complex coding or multi-step research require models to perceive an environment, adapt to feedback, and maintain goals over many steps. The core problem is that most training data is static text, not rich interactive trajectories, so models rarely experience the kind of environments needed to learn how to act. The authors argue that the main bottleneck for agentic LLMs is the lack of scalable, diverse, and realistic environments. Building interactive setups that span many domains, support long-term reasoning, and remain structurally reliable is expensive and ad hoc. Existing benchmarks are narrow and often synthetic, which leads to a simulation reality gap. Models that perform well in toy settings, but fail in messy real-world scenarios. To move from learning what to say to learning how to act, we need a new scale of interactive environments and trajectories. To address this, the paper introduces the Nex ecosystem, a comprehensive infrastructure for agentic scaling. It has three orthogonal components. First, Nex AU is a flexible agent framework that lets you build complex agent hierarchies through simple configurations, scaling up task complexity. Second, Nex A4A automatically generates diverse agent hierarchies from natural language descriptions, expanding the range of domains and tasks. Third, NextGap integrates dynamic real-world environments, such as tools and external systems, to narrow the simulation reality gap and produce grounded interaction trajectories. Nex AU is the foundation for constructing complex agent behaviors. It provides a modular framework where developers can define agents, their roles, tools, and communication patterns via configuration rather than hard-coded logic. This makes it easy to build multi-agent and hierarchical systems, such as a manager agent coordinating several specialized workers. Nex AU is designed to support long-horizon workflows and rich tool use, enabling the generation of trajectories that reflect realistic problem-solving processes rather than single-shot responses. Nex A4A focuses on diversity. Instead of manually designing agent architectures for each new domain, Nex A4A uses natural language descriptions of tasks to automatically propose agent hierarchies and workflows. For example, given a description like conduct deep research on a topic and summarize findings, it can generate a planner agent, a web search agent, and a summarizer agent, along with their interactions. This automation allows the system to cover a potentially unbounded set of domains and tasks, dramatically increasing the diversity of interaction data. NextGap addresses fidelity by connecting agents to dynamic, real-world environments. Instead of operating in closed simulations, agents can interact with tools like code execution environments, web browsers, or document systems. NextGap orchestrates these interactions to produce grounded trajectories where actions have real consequences and can be objectively verified. This helps close the simulation reality gap, making the resulting training data more representative of the challenges agents will face in deployment. Using the environments and trajectories generated by Nex AU, Nex A4A, and NextGap, the authors train Nex N1, an open-source large language model optimized for agentic behavior. Instead of relying solely on static text, Nex N1 is exposed to diverse, complex interaction data that includes multi-step planning, tool use, and feedback-driven adaptation. The goal is to learn a policy that can handle long-horizon tasks and complex workflows, moving beyond myopic next token prediction toward robust decision-making. The paper evaluates Nex N1 on a range of agentic and coding benchmarks, including SWE bench and tau squared style tasks. Across these evaluations, Nex N1 consistently outperforms strong open-source baselines and approaches the performance of top proprietary models on complex agentic tasks. This suggests that scaling up interactive environments and trajectories, rather than just model size, can significantly boost agent performance. Beyond automated metrics, the authors evaluate Nex N1 on agentic coding and web-based tasks, where agents must plan, call tools, and refine outputs. Human evaluations show that Nex N1's trajectories and final answers are often preferred over those of competing models, especially on complex multi-step problems. This indicates that the training on rich interaction data improves not just raw accuracy, but also the quality and robustness of the agent's behavior. The Next infrastructure is also used to build specialized agents, such as a deep research agent that can conduct multi-document investigations, and a paper-to-poster agent that converts research papers into structured presentations. These demos show that the same underlying framework can support complex, domain-specific workflows. The deep research agent, for example, plans queries, gathers evidence, and synthesizes findings over many steps. Illustrating the kind of long-horizon reasoning the system is designed to train. In conclusion, the authors present the Next ecosystem as a comprehensive infrastructure for agentic scaling. By automating the construction of complex, diverse, and grounded environments, they address the data scarcity that limits current agent training. Looking ahead, they envision evolving this into a large-scale reinforcement learning platform, where environments are automatically generated, increasingly difficult, and objectively verifiable. This would create a dynamic gym in which agents can continuously self-improve and master long-horizon reasoning through active exploration and feedback.